Hello, good evening, everyone. Welcome to this problem solving session. We are in this week two, and I hope last week content was clear and uploaded on YouTube. I hope you were able to watch. And if you have doubt from the previous session or previous assignment, you can ask. I will pause for a time, then we can move ahead with the today's session. So if you have doubt, then you can type it either message box or you can just turn on your mic and then start speaking. Okay, so if no doubt, so anytime you can, so if you feel like you have doubt, then you can ask in between the session also. Okay, so yeah, so if you have doubt in between, you can ask for anytime you can raise your hand or just turn on your mic, or you can type in the message box, which is this chat symbol appearing on the bottom right corner of the screen. So let me summarize with this week content. So this week the initially like so for a few minutes there was this discussion on like the effective mass. So the discussion was on effective mass. So what is an effective mass? So suppose a particle or electron, suppose if it is moving without any influence of any force, primarily of electrostatic force, because it has a charge, and the like the electrostatic force is larger compared to other forces like gravity and other thing. So this if without influence of any potential or any interaction, then it will move freely with its mass, and which is 9.1 into 10 power minus 31. So if electrons is moving freely, then this is the electron's mass. One is, but in a real crystal, actually, so the electron is surrounded by this host atom. So basically, like for example, if you take the crystal of silicon, then the silicon atoms are there at the periodic arrangement, and the electrons move under the nuclear nuclear potential of these atoms. So then it experience a periodic potential kind of things which scattered the electron. So so as we have seen in the last week, that this kind of potential is the form is like this. So the we can like this is Coulombic potential, so we can put a form like this, and we can approximate in the chronic pending model this as a rectangular or a square potential. So like this, it will form a periodic potential. So then now the electron does not move. Sorry, I think I am just bit disconnecting. I don't know. Like this is problematic. Yeah. I am sorry for the network glitch. I don't know what is happening with the network. Okay. So now this we can approximate the this Coulombic potential with the periodic potential. So now this we can apply a Bloch theorem. So this potential, like if we call this potential as a ux, then you can like so if this is repeating at the periodicity of a, then you can write ux equals to u of x plus a. So this is the periodic potential, and the electron wave function in the periodic potential forms like see, this analogy is kind of similar you see in like when you have if you have seen signal is in time periodic in the Fourier domains, like the exponential of I omega t terms multiply actually. So if like suppose signal of xt is time periodic with period tau. So x of t equals to x of t plus tau. Then in the Fourier domain, x of omega you can write as a e exponential of I omega tau, and then x of omega. So this x of yeah. So this kind of similar periodicity happens. So you can write the wave function as psi of e exponential of minus I k x psi of say x plus a. So the uh, uh, wave function at the suppose the wave function at this boundary, if you are considering as psi x, then the in the next period it can be it is at psi x plus a, and psi x plus a you can write is like this. And with the Bloch theorem, basically you can uh, as per the Bloch theorem, this is psi of x plus a equals to psi of a x. Then this exponential of I k x will become 1, and then you can write this as an exponential of this I exponential of minus I k x equals to you can write exponential of uh, minus I times 2 pi 1, you can write this. So then you can write this thing. So kx no, this is ka. So at the a potential, so this is ka. So the kx you can write like kx equal ka. So basically ka is 2 pi. If you compare, then k you can try by 2 pi by a. So this the wave function of electrons has the periodicity of 2 pi by a. So this is known as the in the this follows the similar Fourier domain properties. So yeah, so now we digress a bit. So the electrons will see this Coulombic potential, and it will scatter. So the mass of the electron. So to model in a very classical way this uh, quantum mechanical nature of arrangement of atoms, we can model it very classically, so that when the electron moves in the crystal, we can approximate is in with respect to this is basic Newton law. So here instead of free electron mass, we will take the effective mass of electron. So the effective mass can be calculated from the band diagram. So if this is the energy of electrons, this which is given by h square k square by twice m. So m star, let's say. So this at the near the near the bandage. So bandage is basically if you are considering this. So let me draw this clearly. So in the last class what we drawn, so if we you take this, so you can draw the band like this, and then you can draw the band like this and like this. So this minimum of this is known as the uh, is the band gap, and this is known as the band edge. So the electrons, or you can write here also, you can call as a band gap at k equals to 0 position, and basically like your effective mass is your curvature of this band edge at the k equals to 0 position here. So for a very lighter, so here the band can be approximately considered to be a parabolic band, and then so yeah, so now a energy of electrons is given by h bar square k bar square by twice m star. So then, and one more thing is like p momentum of electrons, or any quantum from the de Broglie hypothesis, momentum is given by h bar k, and the in the classical way momentum can be like written as m star times velocity. Okay, so this if this thing is clear, then we can take the derivative of this, and this is dE by dk, and this will become h bar k by uh, m star h bar square k by m star, and then if you take again derivative d2 e by dk square, uh, and this will be equals to h bar square by m star, and you can see like uh, 1 over m star is equals to 1 by h bar square d square e by dk square. So this is basically the E versus E derivative of energy with respect to K, and this is the curvature of this. So double derivative gives you the like how much concave up or concave down your curve is there. So the this thing you can calculate the effective mass within a band, and that can be uh, so that can be different uh, parameters. Yeah. So just yeah. Yeah. So this was the effective mass pictures, and then next was the was considered the intrinsic semiconductor. So in an for example silicon, if you consider and if this is a perfect crystal, so what you can like if you can if you consider the periodic arrangement of silicon atoms, so this forms a covalent bond by nearby four atoms in the crystal, and so this form a bond to nearby four atoms in the crystals, and at equilibrium these bonds continuously breaking, and like and then those electrons release will cause will take part in the conduction and give rise to intrinsic carrier concentration. And the intrinsic carrier concentration is of the order of 10 power 10, and that is like if you consider this concentration with respect to the density of silicon atoms in the crystal, then it is the silicon atom density is 5 into 10 power 22 atoms per centimeter cube, and this is per centimeter cube. So you can see like how much this is 10 power 10, and this is 10 to the power 22, and it is a significantly lower compared to the atomic density of silicon. So to increase this concentration, what we do, we introduce the foreign atoms. For example, which type of conduction we want. We dope either a phosphorus or arsenic or boron. This boron is the group 5 element, and no, phosphorus is the group 5 element, and boron is the group 3 element. So based on that, if we replace one of the silicon atom with the phosphorus atom, then it will have outermost almost 5 electrons. So 4 will take part in the conduction band, other will remain, and that will take part in the conduction band. So you can increase, you can do the this like around 10 power 18, 10 to or 10 to the power 19 order of doping. So you can see like compared to intrinsic sense conductivity, you can increase the conductivity by 10 power 18. So it's 8 order of magnitude higher electrons per centimeter cube you can achieve practically. So this is the effect of doping, and this is very special to semiconductors. Conductor does not show these properties, and they show like if you instead of group 5 element, if you put a group 3 element, then this will remain one nearby silicon will not get bonded, and that will lead to formation of holes. Yeah, so that is the summary. So if you have any doubt, you can ask. I will pause for some time, and then we can move ahead if you don't have any doubt. So you can write in the chat box, or you can just turn on your mic, or you can raise your hand, and then I will then if you don't have any doubt, then we can move further. Okay, so let's move to then if you don't have any doubt, then straight ahead, let's move to the first problem. So yeah, the first problem described, consider a rectangular lattice where the atoms are spaced periodically with lattice constant a. So if we consider the rectangular lattice, let's say this. So these are atoms. So if we move in this direction, so this spacing is a. So uh, so it so with this kind of lattice, actually, if you consider if you consider the Bloch theorem and those periodic arrangement of atom, then the momentum vector is periodic in in the k space also. So if we consider two direction, like this is y, this is x, then there are two momentum directions. So this direction it will be kx, and this direction it will be ky. So the in the momentum space, if you start forming the crystal, then it will be periodic in k space. So if you so with this kind of simple geometry, the periodicity in K will be remains is the same. But in other complicated geometry like FCC or BCC, so FCC in the K space will look like BCC, and BCC in the K space look, I think, like, I am doubtful, but it will look like FCC crystal. So this you can transform into the K space, and the periodicity in the that direction is 2 pi by a. And if you consider in the K space two nearest neighbor, if you consider, so this, so suppose let's if this is in the K space, if this is in the K space, then these are the kx direction, this is the ky direction, and you can this periodicity in that way it's like 2 pi by a. So the Brilliant zone is given by, if you consider two nearest neighbor, uh, if you consider two nearest neighbor, and the like by calculating the perpendicular bisector of two nearest neighbor interaction, then you can form this kind of cell. This is known as the beginner size cell, or this, if you considering first nearest neighbor interaction, then this is known as the first Brilliant zone. And this is because this is the perpendicular bisector, then you can consider this as a like, because this hole is 2 pi by a, then you can consider this as a minus pi by a, 2 pi by a. So this first Brilliant zone extend from minus pi by 2a to uh, uh, 2 pi by a. Similarly, if you consider second nearest neighbor interaction, then you can go up to higher order Brilliant zone concept, and that is not relevant to this subject. So the to answer this question, like the correct answer is periodicity is 2 pi by a in the K space, and first Brilliant zone is minus pi by 2a, pi by 2a, and this is Wigner size cell. Yeah, so if there is any doubt, then I will pause for some time. You can ask uh, if you have any doubt. Okay, so if there is no question, then let's just move to next problem. So consider a intrinsic silicon. So the please emphasis, this is given as intrinsic silicon. The band gap is given as 1.12, which is typical silicon band gap at room temperature. Let the probability that the state is located at the bottom of the conduction band is filled by Fc, and the probability that stated that the at the top of conduction band is Fb. Then which of the following is true? So if you consider a band, then this is, if we see is this the conduction band, and if this is the valence band, and this is the intrinsic energy level EI, and for intrinsic semiconductor, the Fermi level will lie closer to EF. So this will be similar. This will be equals to EF also. So to calculate and this EI is basically mid of the gap, and then we can apply a Fermi direct statistics at this temperature. So for example, this these states are here are the continuous states, and similarly here are the states. We can calculate how many what is the probability of occupying those states. So for that we need to apply the Fermi direct statistics, and which is given as, if you consider in the energy terms, then it is given as like this, and that is like f of e equals to 1 upon x1 plus exponential of e minus ef by kt. So the because now uh, so uh, the probability of occupying, and this is given the probability density function, and then you can calculate the probability with this function. So probability of occupying bottom of the conduction band and top of the valence band is given as, so basically we need to calculate f of ec and f of eb. So this this we can calculate as so and basically we need to calculate the probability of occupying the conduction band is given this, and not occupying is 1 minus of this. So a state can be either occupied or non-occupied. So the it will be given as f of ec is given as f of ec is given as 1 upon 1 plus exponential of ec minus ef by kt, and probability of occupying ev is given as f of eb is given as 1 plus exponential of ev uh, uh, ef ev minus ef by kt. So this is the so ev minus ef is negative. So because ef is lying higher, so this you can, or 1 minus, you can consider probability of not occupying is 1 minus f of ev. So basically 1 minus 1 upon 1 plus exponential of ev minus ef by kt, and if you solve this, then it will become exponential of ev minus ef by kt uh, divided by 1 plus exponential of ev minus ef by kt, and if you divide by ev minus ef by kt, then it will become 1 upon 1 plus exponential of minus of ev minus uh, minus ef by kt. So, or you can write this as 1 upon 1 plus exponential of EF minus EV by KT. So, for intrinsic, so because EF is lying higher in the this case, so for, and you can see because in the intrinsic semiconductor, the Fermi level lies within the band gap. So, EC minus EF equals to EF minus EV is around 0.56 electron volt, and that if you put then like this F of occupying the EC is equals to F of not occupying the EV. So that is the correct answer if you call this as a FC and this is FB. So probability of not occupying is roughly equals to the probability of occupying the conduction band. So the correct answer will be FC equals to SB. So if there is any doubt, then you can ask, or we should move ahead. I will pause for some time. Okay, so if you don't have any doubt, then let's just move further. So, consider intrinsic silicon at temperature equals to 300 Kelvin. What is the Fermi level position relative to bottom of the conduction band? So basically, Fermi level is asked with respect to EC. So NC is given as 3 into 10 power 19 and NI as uh, 1 into 10 power 10. So to calculate, uh, we can calculate, so so bottom of the conduction band. So we can calculate, so the semiconductor is given as intrinsic. So basically, this is if this is EC and if this is EV, then the mid EI is lying around 0.56 electron volt, and what is the Fermi level position with respect to the conduction band? So basically, this EI mid gap level is equals to the EF. In that case, because the semiconductor is intrinsic, then you can find the answer as, so, or you can calculate also. So this is Ni is given. So Ni, so N is basically given as Nc exponential of minus EC minus EF by KT. So that if you put N equals to given as Ni and Nc is given exponential of minus EC minus EF is your, or you can calculate the EC minus EF from here. So we need to calculate EC minus EF by KT. So this, if we calculate, then it will become EC minus, so EC minus EF will become KT ln NC by NI. So if you calculate by the number, you will reach out that it is 0.56, uh, uh, 0.56 below the conduction band. So the correct answer will be uh, uh, will be 0.56 electron volt below the conduction band. So the correct answer will be A. So even like you can guess it like this. I think probably will maybe the gate one number question. So you can directly answer also. It lies within the conduction band, like mid approximate at the mid gap of the conduction band, mid gap of the band gap. So this is, if this is 1.12 electron volt and this is 0.56 electron volt. So you can directly answer, and this always in the intrinsic semiconductor Fermi level lies within the forbidden band gap. So, like in the exam scenario, you can answer this way also. You don't need any calculation. So, suppose like the objective types exam, this is fairly well fair and good method. So, this was fairly simple question. If you have a doubt, then you can ask, or we can move ahead. If there is no doubt. Okay, so if there is no doubt, let's just move to next problem. So consider a N-type silicon at time temperature 3 100 Kelvin. What is the Fermi level position with respect to conduction band age? Nc is given as this, Ni is given as this, Nd is given as uh, uh, given as 3 into 10 power 17. So we need to ask what is the Fermi level position. So if you consider complete ionization, so in the case of complete ionization, you can consider N equals to approximately equals to Nd equals so this if you consider if you consider so, just there is some glitch. Okay, so you can consider the complete ionization. Then you can consider an electron concentration same as equals to Nd, and if you consider that, and then that this you can, and you can write Nc exponential of uh, minus Ec minus Ef by kBt kt. So then if you plug in the value n approximately equals to nd, so this will become nd equals to nc exponential of minus ec minus ef by kt. And if you rearrange it, so this if you bring this down, then you can write ec minus ef by kt as ln nc by nd. Then you can calculate EC minus EF equals to KT ln NC by ND. So if you plug in all the values, so NC is given as 3 into 10 power 19. So KT ln NC is given as 3 into 10 to the power 19, and this is given as 3 into 10 to the power 17. So now if you calculate, then it will become uh, so then it will become this will become uh, kt ln 10 power 2. So then you can calculate this is 2 multiplied by kt uh, ln 10, and this is approximately 60 millivolt. So this you can calculate. This will be around. So it will be 2 multiplied by 60 millivolt. So this will be around 120 millivolt, and this will be around 1.212 electron volt. So the approximately the correct answer you can consider uh, like the 0.15 electron volt below the conduction band. Above the conduction band is not possible because like this the doping is significantly smaller compared to the NC, and the correct test is to tell because This formula is valid for Maxwell-Boltzmann hypothesis, and this is valid only of if EC minus EF by KT is greater than 3 actually. So you see, like here this is 0.12 electron volt and KT is 25 milli electron volt. So this is EC minus EF. Even here we find that it is much larger compared to 3 times KT, which is 75 milli electron volt. So our assumption and this formula is valid. So the conduction band will be below only. Will not the Fermi level will not approach to the conduction band, and this approximation is valid in this case. So if you have any doubt, then you can ask, or I will wait for some time. Okay, so if you don't have any doubt, let's just move to next problem. So consider the Fermi direct distribution function Fe with the different temperature. Which of the following statement is true? So the Fermi direct distribution f of E is given as 1 over 1 plus exponential of E minus EF by KT. So two case. So E is less than when E is less than EF, then E minus EF is negative. So this exponential term is negative. So what will happen? So this bottom terms is negative. So bottom this is negative, and and for E equals to EF, this exponential term is 0, and this total exponential of this will become 1, and f of E will become point 0.5. So this is the point 0.5 value, and for E less than EF, this term is negative, and when this term is negative, so this will become smaller, and this f of E become larger the compared uh, uh, to the EF values. So this will increase. So that's why this form is coming. And for E greater than EF, this term is positive. For larger energy, we will have the f of E less than point 0.5. For lesser energy, we will have f of E greater than point 0.5. But in any case, in any case, I don't know this network is. So in any case, this will be lesser than 1 because this is the probability. So and as you increase the temperature, so so for let's consider this term, exponential of e minus ef by kt. So for two case, let's say when e is greater than ef, then this the exponential argument is positive. So if you increase the temperature, so if T2 is larger than T1, so this exponential term become smaller, and basically when this becomes smaller, then then your uh, if this term becomes smaller, and then your this f of e will get increased. Similarly, for e minus ef less than point less than kt, less than 0, then this term is negative, and if you increase the temperature for negative term, then the bottom term will become smaller, and the corresponding f of e will get increased. Bottom term will become smaller, and f of e will get increased. So yeah. So then f of e will, so the correct answer for this is the temperature T2 is larger compared to the temperature T1. So that you can solve even yeah. So case wise, like two case you need to consider whether your E minus EF is positive or EM minus EF is negative. So based on these two conditions, you can calculate those things. You can calculate what is the trend you will expect in the Fermi function. So if there are any doubts, you can ask, or if there are no doubts, you can. Uh, okay, so let's move to next problem. Uh, consider a three typical semiconductor A, B, and C with band gap EGA, EGB, and EGC, whatever given at this, and this. So the intrinsic carrier concentration of material as a function of 1 by T is shown in figure. So which of the following is true regarding their band gap? So basically, intrinsic carrier concentration you can calculate as this is Ni is Ni is Ni square is or Ni is square root of Nc times Nb exponential of minus Eg by 2 kt, and if you take log of this, log of Ni log of ni, then this will, if you treat this as a constant, or this is slowly vary compared to the exponential term, then you can take this as a constant. So log of c minus eg by 2kt. So if you consider this, the variation, sorry, this internet is bit notchy. It's not bit notchy, it's notchy only. Yeah, so this is so Eg by 2kt, and if you plot the Eg with respect to this, then this slope is defines your band gap. So this higher the slope, higher your band gap. So the Eg will of C will have highest slope. So this is the highest slope, and this is the lowest slope, and this is the midland. So so the Eg is lowest. So so this A, so this is EA is lowest, and EB. So the correct answer will be A, EA, EB, and EG. EG, EA, EB, and EC. So EC will have the highest slope, and uh, I don't know. It's not matching. So yeah, so the correct answer will be A. And so if you have any doubt, then you can ask, or we can move ahead. So let's move to next problem. So this is considered a two degenerate non-degenerate semiconductor A and B with band gap EA and BB. The resistivity of these two material reduced with respect to temperature as shown in figure. Which of the following is true regarding their band gap? So basically, resistivity rho is inversely proportional to the carrier concentration, and because these are the intrinsic semiconductors, so this resistivity is inversely proportional to the Ni, and if you take a log of rho, that will be proportional to log of Ni minus, and if you calculate in the last we calculate the log of Ni, so it will be equals to minus of some constant plus log of uh, uh, Eg by 2 kt, and if you calculate this, so uh, the the which have the higher slope will give you the more with the higher slope, or this, because this is the negative zone, with the higher slope you will get a larger band gap, and with the lower slope you will get the smaller band gap. So band gap of A will have higher band gap compared to band gap of E. So Eg of A will be higher compared to Eg of B. So that is your answer. So the correct answer is B1. So yeah. Okay. So if you have any doubt, then you can ask, or we can. Okay, so this is the next problem is in a non-dig. This is gate appear in very recent gate 2022 exam, and this is the non-degenerate bulk semiconductor with electron density this, with the value of EC minus EFN is 200 milli electron volt. So EC minus EFN is given as 200 milli electron volt, where EC and EFN denote the bottom of the conduction band and the Fermi energy level, respectively. Assume that the thermal voltage is KT is given as 26 milli electron volt or 0.026 electron volt, and the intrinsic carrier concentration Ni is given as 10 power 10 per centimeter cube. For n equals to 0.5 into 10 power 16, the closest approximation to the value of EC among this is given option. So so You can calculate so you can calculate n as ni exponential of ec minus efn divide by ec minus efn. Just wait. No. This was so n you can calculate as nc exponential of ec minus efn by kt, and for for so now it's given the concentration is changed to zero point 0.5 into 10 power 16. So so this is given as for 1 into 10 power 16 nc exponential of ec minus efn is given as zero point 0.2 electron volt divided by 0.025, and if you take the ratio, then you can calculate 1 10 power 16 divided by 0 0.5 into 10 power 16. nc will get cancelled, exponential of 0 0.2 electron volt by 0.025 divided by exponential of ec minus efn divided by kt. So if you calculate this, so if you exponential of ec minus efn by kt equals to uh, this will become zero point 0.5 into 10 power 16 divided by 10 power 16 uh, exponential of zero point 0.2 divided by 0.025, and this 10 power 16 will get cancelled. It will become 0 0.5 exponential of zero point 0.2 by 0.025, and this, if you take log both sides, then you can get the value of ec minus ef, and which will come around 0.218 electron volt or 218 milli electron volts. The answer was asked in 218 milli electron volt. So that is the correct answer, and option C is correct. So this was fairly simple question. Yeah. So if you have doubt in the problem up to now, you can ask. I will wait for some. Okay, so let's move to next problem. Okay, so let's move to next problem. Consider a silicon sample with a doped with 10 power 16 phosphor 10 to the power 17 phosphorus atom. Assume the donor energy level is 45 milli electron volt below the EC. So if we draw this, so this is EC, this is EV, and this is EI, and this is 45 milli electron volt. This is 45 milli electron volt. This is ED, donor energy level for phosphorus. Uh, at t equals to 0, the dopants are not ionized. So what will happen is the t when the temperature is 0, the all the dopants are in their donor energy level, and those are not ionized because there is no thermal energy. So all the dopant will be at their dopant side, and the electron the semiconductor will be intrinsic. At higher energy levels, some of these dopant will move into the conduction band that will take parts in the conduction. So this will become here, and here this hole will become. So this will become empty donor, and it will become immobile charge ion or dopant level ionization are there. So depending on the temperature, like in most of the cases, we assume this assumption that ND the number of ionized dopant are full. So basically, the number of electron donated by these dopants are approximately equals to ND. But here is not the case. We need to calculate how much is the dopant energy level. How much fraction of dopant can be ionized. So the dopant ionization is given by the same as the Fermi direct distribution. So Nd plus or Nd plus by Nd you can calculate as 1 upon 1 plus exponential of Ed minus Ef by Kt. So we are not consider degeneracy of two of our electrons or this is the simple case. So the now Ed minus Ef we know. So 1 upon 1 plus exponential of this is 45 milli electron volt and this is 25 milli electron volt. So this will become so this will become 1 upon 1 plus exponential of 9 by 5. So this will become 9 by 5 and this will become 0.18. So this will become 1 upon 1 plus exponential of 0.18, and this if you solve by that, the then basically if you get this if you solve by this you will get around 0.023, and if you calculate in the percentage then this will become around 2.3%. So that is the correct answer, and this was the I think one of the gate problem in recent past year. So yeah, so let's move to next problem. In an semiconductor, the Fermi levels, and this is the gate 2023 problem, very recent one. In a semiconductor, the Fermi energy level lie 0.35 above the valence band. The effective density of state in the valence band is 300 Kelvin. Is one, so Nv is given as 1 into 10 power 19. The thermal equilibrium hole concentration. So N as it's asked in 400 Kelvin. What is the hole concentration? So at room temperature we are given effective density of states, and uh, we need to find the hole concentration uh, uh, for uh, for 400 Kelvin. And we know from the equation NB is directly proportional to T to 3 by 2 power of temperature. So we can so the whole concentration is given as NB times exponential of EV minus EF by KT. So then P at 400 Kelvin. So uh, this so and so you can calculate the NB at uh, 400 Kelvin will be so NB at 300 Kelvin is given. So you can calculate this this will be a factor of 3 by 2, so temperature 3 by 2. So this is let's say you can calculate whole concentration 300 Kelvin will be given as some constant factor time temperature 300 Kelvin power 2 3 by 2 exponential of EV minus EF is given. So like this is given as 0.35 electron volt, and this is KT is 0.025 for 300 Kelvin. For 400 Kelvin, you need to calculate. So then this is C and this is 400 Kelvin, power 3 by 2 exponential of 0.35 electron volt divide by this also will become so it will become so at 300 Kelvin this is 0.025 and at 400 Kelvin it will become so at 400 Kelvin it will become 0.025 multiply by 400 divided by 300, so it will become so it will become zero point 0.1 by 3. So this will become zero point 0.1 by 3. So you can point at 300 it's given. So so the this at 300 it's given. So just wait. So this we can calculate. This is given at 300. We calculated. So if we take the ratio, then we can calculate this P of 400 will be equals to 400 divided by 300 power 3 by 2 multiply by into 10 power 19. This constant term or this is NV at 300 and then exponential of minus 0.35 divided by this is will be minus and this is 0.026 multiply by 400 divided by 300 and if you solve this will you will get to 6.2 into 10 power 14 per centimeter cube. So that is the correct answer and which so it is so 63. So the answer is given as 10 power 13. So you need to adjust a decimal point. So approximately the closest matching answer was around 63 point zero. So this was the last problem for today. So yeah. So sorry. My net was not bit, it was quite notchy. So there was lot of disruption in between, and I hope it will be better next time. So thank you so much for listening this session. So if you have any query, I can answer. So you can type in the chat box, or you can raise just your hand, and then I can answer. Or you can just turn on your mic, and then I can answer the query. So I will wait for some time and then if you have some doubt, then you can have. Okay, so if we don't have any query, then hopefully because net is bit notchy today, we can end this session. So we will meet next time, s- same day, same platform next week. I wish you a very good, happy time and keep learning. I hope you will get benefit from this session. Thank you so much. We will meet next time, same platform at the same time. See you. Bye. Have a nice time. Good night. And I can end this call. End this call.